Today's topic is kinetic theory of gases. Under this topic, we will be mainly dealing with ideal gas. What is an ideal gas? An ideal gas is the one which follows many of the standard gas laws, which we'll study today. The first law is PV is equal to nRT. What is this? You have a vessel. You have some gas here, whatever amount it is, doesn't matter. The gas has a pressure P, it has a temperature T, and N is the number of moles of gas. What is number of moles? I think you already know it, but just for the sake of clarity, if you take 2 grams of hydrogen or 32 grams of oxygen, both contains 1 mole of gas. Now there are certain properties regarding 1 mole of gas. At STP, which is standard temperature pressure condition, 1 mole of gas contain Avogadro's number of molecules or atoms, as the case may be, and its value is approximately 6.02 10 to the power 23. This is one property. Second property is that this 1 mole of gas, will occupy 22.4 liter of volume. These two are very important properties of ideal gas. So if we come back to this equation, this means okay, let me define what is R. R is universal gas constant. It is a constant. T is absolute temperature. So over this equation, PV is equal to nRT. What it says is, if we take n number of moles in a gas, then if the gas is at temperature T, then the pressure and volume is given by this relationship. So in this, basically there are 3 variables: pressure, volume, and temperature. If you know any 2 of them, you can always find the third one, given that you know the number of moles, right? Now we talk about average velocity of molecules. It is found that PV is equal to 13 m v square. P and V we have already seen. This is pressure. This is pressure. This is volume. And what is M here? M is the total mass of gas. And what is V? V is the average velocity of molecule or atom. Why are we saying molecule or atom? Because a gas can be monoatomic or diatomic. For example, hydrogen, oxygen, chlorine, they are diatomic and there are two atoms of hydrogen combined to make one molecule. So if we have hydrogen, oxygen and chlorine, these we will call molecules. Then kinetic energy, let's call it K, this is equal to summation of kinetic energy of individual atoms or molecules. This can also be written as V is equal to 2/3 what is K? K is total kinetic energy. Or we can write K as 3/2 PV. Total kinetic energy, this is pressure, this is volume. Another interesting relationship is half M1 V1 RMS square is equal to half M2 V2 RMS square. What it means is if there are two different gas particles, one with mass M1, another with mass M2, and this atom or molecule has a RMS, root means square, velocity as V1 square RMS, and similarly this has V2 square RMS, then they are equal. So what it means is kinetic energy in terms of VRMS of any two atoms or molecules is same. Now let's understand what is velocity and what is RMS. Now velocity is a vector quantity. The vector can be this way, it could be this way, it could be this way, this could be a negative way. Now, if in this direction the velocity is v, then in this direction the velocity will be negative v. But if we want to take the quantity of magnitude of v, then what we do is we square it up and take the under root. This is for 1. So for example, this is for particle 1. Then we do it for, what we first do is we add the v1 square plus v2 square plus v3 square and so on and so forth, and divided by n. This is our square, average square velocity. Now, if we again want to see how does it compare with our velocity, since we have already taken root, what we do is we take the under root of this. And that is why the name root mean square. It actually means root of mean of square. This quantity is mean of square. And then when we do under root, it is root or mean square. So the advantage is that the signs are, whether it is negative, positive, they are all absorbed when we do a squaring. Now next is Graham's law of diffusion. Let us say you have a vessel which is separated by a chamber which has got perforations. This is gas 1, this is gas 2. And what will happen? Gas 2 will try to mix with gas 1 and gas 1 will try to mix with gas 2. This process of mixing of one gas with the other is called diffusion. Here gas 2 is trying to diffuse into gas 1, and here gas 1 is trying to diffuse into gas 2. So both the process go simultaneously. And there are certain relationships in which is R1, R2 is equal to rho 2 by rho 1 under the rule, which means rate of diffusion of gas 1 into gas 2 divided by rate of diffusion of 2 into 1. Rate of diffusion of 1 into 2 divided by diffusion of this gas into 1 is given by the inverse of their densities. This is density of gas 2. This is density of gas 1. This basically means lighter the gas, faster it will diffuse into other one. Here the condition is that the two gases are at same pressure and temperature. Both these gases, gas 1 and gas 2, should be at same pressure and temperature. Same pressure and temperature. Next is Dalton's law of partial pressure. Let us understand what is a partial pressure. Let us say you have a vessel in which you have gas 1 and then you have gas 2, which is represented by these square blocks. This is gas 1. This is gas 2. Or maybe there may be more than 2 gases. This is the third one. Let's say this could be gas 3. Then what happens is each of the component of these gases will exert their own pressure separately, which is independent of one another. And the total pressure here will be sum of the individual pressures, which means that total pressure P in this vessel will be equal to pressure exerted by gas 1, partial pressure, plus partial pressure exerted by gas 2, plus partial pressure exerted by gas 3, and so on and so forth. This partial pressure of one is independent of partial pressure of the others. Now, coming back to detailed treatment of RMS velocity. V RMS is equal to 3P by rho. This is found by empirically. Most of the relationship in gas laws are empirical. Okay. It is also equal to VRMS can be written in many forms. One is this one. Second is, it is 3 kT by m, where K is Boltzmann constant, T is absolute temperature, and m is the mass of each molecule or atom, as the case may be. It is also written as 3 RT divided by m0. R is gas, universal gas constant. T is absolute temperature. And MO is molecular weight of the gas. This is all about VRMS, root mean square. Velocity, which is root mean square, RMS in short. And the average velocity is, why we average velocity? Because in gas, molecules are going everywhere with various velocity. The velocities are not constant, but if we take an average velocity, it comes to We have already seen R, we have already seen T, M0 same as molecular weight of gas. Now, as we have seen that when we put the gas in particular space, then various various atoms or molecules have random velocities. Then, if we try to find the statistics of these velocities, it is found that the most probable velocity is given by this formula, where K is Boltzmann constant and M is the mass of each molecule. Now, you must have studied in statistics sometime or the other that if you plot height of children in a class versus their numbers, you get something like a bell curve. And this is the point where most of the students have the height. This is also called the mean height. Now, taking this analogy, if we plot the velocity of our molecules or atoms on a scale which is dn dv, now what is this dn by dv? dn by dv is the number of molecules or atoms which have velocity between v and v plus dv. Now, I'll use the space here, I'll redraw it again. This is our v. This is our dn by dv scale. Then the curves look something like this. For a particular temperature T1, let's say, for example, this is 150 degrees centigrade. If we increase the temperature, what will happen? This velocity is definitely going to increase because at high temperature, the agitation is more. So this may be at T2, which is, for instance, is 20 degrees centigrade. So this is our distribution of velocity, and this we call as most probable velocity. It's a function of temperature also. Now, in container, we know there are particles here, everywhere there are atoms or molecules. Now, suppose this molecules goes this way, it encounters another molecule and it will hit it. Yeah. So we define certain terms called tau. Tau is the time. See, this particle may hit this atom or molecule may hit another one here. Then after hitting, it may take another path. And after some time, it may, so now this is particle P1. It hits T particle or molecule 2. Then it goes this way and hits another atom or molecule 3. So the process goes on. So we define tau as a time between two successive collisions. And it is given as n is the number of atoms or molecules per unit volume. Per unit volume of gas. V is the velocity and d is the diameter of atom or molecule. Okay. If that being so, we define another term called free path. When this atom or molecule 1 starts its journey, until it hits atom 2 or molecule 2, it has a free path. There is nothing in between. So this distance we call as L or free path. So obviously free path is going to be velocity time tau. This is the time taken before this paradigm of free path is broken. Means it there's somebody else who comes in the path within time tau, and within this time with velocity v, it has traveled so much of distance, which is called free path. Mean free path, which should have been which is given by this relation on this, is a refined, a more accurate version, which is mean free path L is equal to 1 by root 2 times n pi d square. This is a more accurate relationship. Now we have seen R, which is universal gas constant, and K, which is Boltzmann constant. There's a relationship between them, and which is R is equal to Na into Kb. This is Avogadro number. This is our Boltzmann constant. And this is our universal gas constant. Now, all these relationships we have seen, assuming that our gas is ideal. But is there any non-ideality in the gases? Yes, it is. There is. All gases don't behave perfectly as ideal gas. So, if we plot pressure versus PV or nRT, now we know that PV is equal to nRT. So, PV by nRT should be a constant value always, but it is not. We have seen for different temperatures, the curve may look like this is for temperature T1, this is for temperature T2, this is for temperature T3. And this is the actual PV by nRT, which should have been for ideal case, but it is not. So, as you see this, it is very evident that real gases, we're talking about real gases, not ideal gases, real gases approach ideal gas at low pressures. We've seen all this curve, this curve, and this curve, this curve, this curve, this curve. They are all meeting at this point, which is perfect point, PV by nRT. But they deviate as we increase pressure. Yeah. And if you see this curve, T1 curve is more flatter compared to T2 or T3 curve. So we know T1 is greater than T2, is greater than T3. What it means is, as the temperature increases, the real gas, this should have been our curve, the dotted root should have been our curve for, this is for ideal gas. The real gases at high temperature tend to behave like ideal gas. So we can conclude that real gas tend to become ideal gas as we decrease pressure, at low pressure, and like here, if we increase our temperature, again it tries to come closer to ideal gas and high temperature.